Bellman Ford Algorithm. Let us see what is Bellman Ford Algorithm and how it works. Bellman Ford Algorithm, it is a graph traversal algorithm which is used for finding the shortest path from a single source vertex to all other vertices in a graph. So wherever the vertices be there, we'll find the shortest path from the source vertex to all other vertices. At this point, you can have a doubt. This is the same work that Dijkstra's algorithm is doing. Then, why should you have Bellman Ford algorithm and how is this better than Dijkstra's algorithm? The answer is Bellman Ford algorithm can work even if there are negative weight edges in the graph. In case of Dijkstra's, we learned that if there are any negative weight edges in the graph, Dijkstra's algorithm cannot work. But in case of Bellman Ford algorithm, even if you're having negative weight edges, still this algorithm will be able to find the shortest path to all the vertices from single source vertex. Next question is, what happens if there is a negative weight cycle? In this case, Bellman Ford algorithm can detect the cycle, but in this case, you won't be able to find the shortest path. So there are two things here. One is, in case there are negative weight edges present, Bellman Ford algorithm is useful for finding the shortest path. In case there are negative weight cycles present, then Bellman Ford algorithm is useful for detecting the presence of this negative weight cycle. This is the point. So when should you use Dijkstra's and when should you use Bellman Ford? Dijkstra's is better in case of time complexity. So whenever you don't have negative weight edges, you should go for Dijkstra's algorithm. If there is negative weight edge present, then anyway Dijkstra's is not going to work. That is where you should use Bellman Ford algorithm, right? Let us see what is the key idea behind Bellman Ford algorithm and how exactly does it work. The key idea is very simple. You have to relax all the v minus 1 edges, all the edges v minus 1 times, ensuring that the shortest paths are updated. So what is the logic of updating all edges v minus 1 times? The logic is like this. What are you going to find? You are going to find the shortest path. If you are having v vertices, let us say this is your graph, you are having these vertices, these 5 vertices are the maximum number of edges that can be present in a shortest path from any vertex to any other vertex is v minus 1. Why is it like this? The reason is, let us say I'm starting from here. I want to find shortest path to some particular vertex. Let us say I already have v minus 1 edges in it. Here v is 5. I have 5 vertices. So I'll draw 4 edges here. Let us say one edge is this, second edge is this, third edge is this, and fourth edge is this. At this point, I have v minus 1 edges. If I add one more edge anywhere, wherever I may add one more edge, let us say here I added, the problem is it will form a cycle. If you are forming a path and that path is having a cycle, then you have an option to remove that cycle and find a shorter path. Why is this? Because let us say you started from here and you want to reach here. What am I doing? Let us say I went like this, then I came here, came here, came here. Again I went like this and reached here. Here I have an option to remove this cycle and instead do not take that cycle. I'll simply come like this and come here. Whenever you have a cycle in graph, you have an option to not traverse through that cycle and find an even shorter path. That is why the shortest path from any particular vertex to any other vertex in any graph should not have a cycle. This rule will automatically state that maximum number of edges that are possible in a graph in a shortest path from any particular vertex to any other vertex is at max v minus 1 edges. So maximum number of edges there should be v minus 1. Keeping this in mind, if you think back, it is clear that maximum number of edges present will be v minus 1. Here, each relaxation in Bellman Ford algorithm refers to adding one edge in your shortest path. So when you have v minus 1 relaxations, that means you added v minus 1 edges to your shortest path. If you add one more edge, that won't be the shortest path because of the rule we stated prior to this. That is, it will form a cycle, then it won't be the shortest path. Because of this, maximum possible requirement is v minus 1 relaxations. So the logic behind Bellman Ford algorithm is you will relax each edge v minus 1 times. The next question is, what is relaxation? Relaxation actually means you are trying to see if this edge can be part of the shortest path. If it can be, then while relaxing this particular edge, let us say I am relaxing this edge. While I am relaxing, I'll see what is the weight of this edge. Let us say 2 is the weight of this edge. I will see if I add this edge to the shortest path, will it be decreasing the existing shortest path length or not? This is what I'll be calling as relaxation. If it is decreasing, then I will update the shortest path. This is how it works. So we'll see what exactly is the algorithm. Then it will be clear to you what is the relaxation and how it is working. Okay. Let us take one graph for example and we'll see each of the steps in the algorithm. At this point, you will clearly understand what is relaxation. Okay. I'll just draw a random graph here just to show you how it is working. Okay. I'll have edges A, B, C, D, E. The first step in Bellman Ford algorithm is you should set the distance to your source vertex as 0. So whatever be the source vertex, distance of source vertex, this should be 0. Let us say my source vertex is A. Then I'll say distance to A, d of A is equal to 0. This is my first step. Why should I make this 0? Because based on this, I am going to find distance to all other vertices. So at this point, distance to A is 0. What is my next step? Distance to all other vertices. They should be made as infinity. So distance to all other vertices, they should be infinity. Why is it infinity? Because at this point, I did 0 relaxations. When I did 0 relaxations, that means the maximum number of edges that are presently in my shortest path. At this point of time, I am having 0 edges in my shortest path. So with 0 edges, I can only stay in the source place. I can't go anywhere with 0 edges. So to the source, distance is 0. So that is already updated. But if I want to find distance to any other vertex, I should have at least one edge in my shortest path. So that is why as of now, to all other vertices, I will say it is infinity. The distance to all other vertices will be infinity. What is the next step? This is where I am going to start relaxation. So second step is relax all edges. Relax all edges v minus 1 times. So let us see how exactly this relaxation is working. I will pick each edge. I'll pick each edge uv. uv means this edge is going from vertex u to vertex v. I will pick every single edge in the graph uv, which is having a weight w. What will I do? I will update the distance to vertex v if a shorter path is found by including this particular edge. This is the logic. How will I see that? How will I see if this particular edge can be included in order to find a shortest path to v? In order to do that, I will check whether the distance to u is already existing. So whether the distance to u plus the weight of this edge is uv, weight is w. So if the distance to u plus the weight of this edge, if this is less than distance to v, what does this mean? Existing distance to v, as it can be infinity, it can be anything else. Whatever be the existing distance to vertex v, that is a value greater than the existing distance to u plus the weight of edge uv. This means I can make this value as new distance to V. This is what is called as relaxation. If I can find a shorter path to this vertex V, then I will say my distance to V is updated to this value, right? So this is what I'll call as relaxation. If this happens, what will I do? If this condition is satisfied, what should I do? I should update distance to V. This should be distance of U plus the weight of edge UV. This is what I should do. I should repeat this relaxation V minus 1 times on each of the edge. When I say V minus 1 times on each of the edge, that doesn't mean pick one edge, relax V minus 1 times, then pick another edge V minus 1 times. No, you should relax each edge once, then relax each edge once, again relax each edge once, like this, repeat V minus 1 times. Okay. So after doing this, is there anything more to be done? Because once I relax all the edges V minus 1 times, at this point I should already have the shortest path to all the vertices. That is, from the source vertex, shortest path to all the vertices. Is there anything more to be done? Yes, there is something more to be done. What is to be done? We have to see if there is a negative weight cycle present. How will you see that? In order to detect a negative weight cycle, what you will do is, you already did the relaxation V minus 1 times. After this, try one more relaxation. For a Vth time, try to relax all the edges. This time, if you are able to detect any edge UV with a weight W such that distance to U plus the weight of this edge is less than distance to V, what does this mean? If after relaxing V minus 1 times, still you are able to find some particular edge UV with a weight W such that distance to U plus the weight of the edge is less than distance to V, that means you can do one more relaxation and still find a shorter path. This also means the graph contains a negative weight cycle. This is the point. How did I say it contains a negative weight cycle? That is because after V minus 1 relaxations, if I am able to do one more relaxation, that means I am considering a shorter path which is having V edges. Previously it was V minus 1 edges. This time I am saying it is having V edges. If it is having V edges, we already discussed, that means it has some cycle, right? If it is having some cycle and using that cycle you are able to find a shorter path, that means this cycle is a negative weight cycle. And what is the problem with a negative weight cycle? Let us say this cycle is having edges 2, minus 1 and minus 2. This is a negative weight cycle. If you start from here, you traverse like this, what happens? Total weight is 2 minus 1 minus 2, which is minus 1. If you traverse through this negative weight cycle once, you have minus 1. If you traverse twice, it will be minus 1 plus minus 1, which is minus 2. If you traverse through negative weight cycle again, it will be minus 3. Like this, if you keep traversing through this cycle 1000 times, it will be minus 1000. So you will never be able to find a shortest path if there is a negative weight cycle present, because you can keep cycling and the shorter path distance will keep decreasing. This is why whenever there is a negative weight cycle, you will not be able to find shortest path. So what will you do? In case of negative weight cycle, you will just detect it. That is what you are doing here. If Vth relaxation is giving you a shorter path, that means the graph is having a negative weight cycle. If it is having a negative weight cycle, you cannot find the shortest path. Negative weight edge is okay. In that case, Bellman Ford algorithm can still find the shortest path. But if there is a negative weight cycle, it is impossible to find the shortest path. That is why we are just detecting. So these are the steps. First, you have to initialize source vertex to 0 and all other vertices to infinity. That means distance to all other vertices as infinity. Then you have to do relaxation V minus 1 times. Once you do that, what is relaxation? You have to check for every edge whether adding that edge will make the path to V shorter. So after you do v minus 1 relaxations, you will have the final answer there, because at this point, whatever is the distance to each of the vertices, that will be the shortest path possible from source vertex to that particular vertex. Again, if one more relaxation is possible, that means there is a negative weight cycle present in this particular graph. So what are the final points that you understood from this Bellman Ford algorithm lecture? First point is, you should always prefer Dijkstra's algorithm for finding the shortest path, because that is single source shortest path. From single source to all other vertices, if you want to find, you should always prefer Dijkstra's algorithm because it is having a better time complexity. In case you are having negative weight edges, that is when Bellman Ford algorithm is useful. But in case of negative weight cycles, Bellman Ford algorithm will still detect the negative weight cycle, but a shortest path, as we discussed, is not possible in case of negative weight cycle case. Dijkstra's is better because Bellman Ford is slower, but Bellman Ford is better in handling negative weight edges. So this is what you have to know about Bellman Ford. One more thing I'll tell you about Bellman Ford is that I told you have to do V minus 1 relaxations, but there is a catch. You don't have to do V minus 1 relaxations every time. In case none of the distances to your vertices get updated after 2 iterations, that is, you have some particular values, you did relaxation of all edges, and then before relaxation and after relaxation, distance to all the vertices are remaining the same. That means if you do more relaxation, it will still remain the same. Why is it? Because you did relaxation of all edges, there is no change at all, means none of the edges is adding anything more. So if you again relax one more time, you are going to do the same procedure again. Again, if you relax one more time, it will be same procedure again. So there is no point in relaxing again and again if you did one set of relaxation on all the edges and there is no change in the distance to any vertex. So this is the final point you have to keep in mind. Whenever ideally you may have to do V minus 1 relaxations, but if there is no change after relaxing all edges in one iteration, then you can stop it, right? Because there is no more improvement possible. You already have the shortest path. This is it about Bellman Ford. Next lecture, what we'll do is, we'll take a graph and see exactly how Bellman Ford is working, how in each iteration the distance to each of the vertex is changing, and how we are reaching the final solution. After that, we'll see the algorithm, how to write the algorithm for this Bellman Ford, how can you write code. Then we'll see time and space complexity analysis, and these things we'll see in the upcoming lectures.